Hello everyone and welcome back to Senior Mathematics. My name is Victor and this video is going to be different from everything that we've done so far. We are not going to be solving an equation or just sketching a graph. So instead of that, we're going to be proving that a mathematical statement is true for every single positive integer. The tool that we're going to be using is called mathematical induction. What is it? What can I use as an analogy? So you can think of basically an infinite row of dominoes. If I show you two things, first the first domino falls, of course. So if I show you like dominoes and stuff like that, it's gonna look basically something like this. So the first one falls, the next one will fall, the other one will also fall as well. It knocks over the next one, and every domino in the entire infinite roll must follow as well. So first domino, we have the base case, one domino knocking over the next. That is going to be the inductive step, and so together these are going to prove the statement for every positive integer. I hope that analogy really does help. Hope. But I think an example would help more. So let's look into the first one, the box number one, the base case. Proving the statement is true for n equals 1. This is usually pretty straightforward, arithmetic. You don't want to change anything here, just put into like n plus 1. You don't want to put like something n plus 2. That will be for the inductive hypothesis or something like that. So then look at box number 2. The inductive hypothesis here. Now, this assumes the statement is true for some arbitrary positive integer k, of course. Now, we do not prove this. The proving step will be in step number 3, but we assume this is true. This is going to be the step that feels pretty weird, but you're only assuming it for one specific value, which is k. And then in box number 3, which is the inductive step, you want to be using the assumption from box number 2 to prove the statement is true for k plus 1. This is where the algebra will happen, and this is where our first habit comes into play. What you want to do is state what you assume and show what follows. State what you assume is usually the second step, and then show what follows is usually the third step. Now, what I want you to do is what we need to go into step number 1, find the base case, of course. So let's just zoom that out. So the base case, we need to prove this. So our base case is n plus 1. So n plus 1 here. I'm going to write in both places, so to save some space, of course. Now, I'm going to look at the left-hand side and the right-hand side, of course. So the left-hand side here, the left-hand side for the base case is going to be equals to 1. The right-hand side is 1 multiplied by 1 plus 1 divided by 2, and that would give us 1, because this is 1 multiplied by 1 times 2, and 2 divided by 2 is usually 1. So is the left hand side equals to the right hand side? Yes. That is our first domino right there. So when n equals 1, left hand side is just 1, right hand side is just also 1. The formula works for the first base case, which is step number 1, so the first domino will fall. Now, for our next one, we have to assume that this is true for n equals k. So we need to assume that, okay? So if we're assuming this, what we do mean by assumption is that we're going to write this in our notes. We're going to write 1 plus 2 plus 3 plus dot 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 plus k equals k multiplied by k plus 1 divided by 2. We're basically substituting n with k here. This is the part where we are assuming it. Again, state what you assume, which is the second step. The third one is to show what follows. That's the next step. We do not know this is true. We're assuming it. Okay. And for our last step, which is the inductive step, we need to prove for n plus k plus 1. So we have to substitute n with k plus 1 here. So it means that with this being true, you have to prove this. 2 plus 3 plus dot 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 plus k plus 1 equals k plus 1 multiplied k plus 2 divided by 2. If this is true, you have to also prove that this down here is also true. This is where you show what follows. We need to show that formula holds for k plus 1. And so this is where we're going to be writing the algebra. And so what we need to do is we need to look at this and write. So we need to prove that the left hand side is equal to the right hand side. So let us just start at the left hand side. This is working space for this, but this is honestly not enough. So let me just write this whole thing all over again. So 1 plus 2 plus 3 looks much more clean. There's much more space. K plus 1, k plus 2 divided by 2. And what we need to, that is the something we need to prove. So let's just look into the left hand side first. I'm going to zoom out just a little bit. Left hand side. Now, what does it equal to? It equals to 1 plus 2 plus 3 plus dot 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 plus k. Okay, we're going to group this together, and then we're going to isolate the k plus 1 to be the last term, or the last one that's going to be added, because we want to utilize this as equals to k multiplied by k plus 1 over 2 plus k plus 1. Why is this the case? Because we just assumed that 1 plus 2 plus 3 plus dot 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 plus k equals to this. So we are merely substituting the very long part here into the part that we just, the multiplication part, down here. So we're substituting that. So this is the substitution, the substitute hypothesis. Now we're going to, of course, we're going to have to simplify this. So we're going to need a common denominator. We need 2 of these, because if we don't have that, there will be half of that, and it's not really half. We need a common denominator here. So when we have this, we will have the common denominator, which is 2. Let me just write that out. And what we will have is k squared plus k plus 2k plus 2k plus 2. And this will give us k squared plus 3k plus 2 divided by 2. Now, if you know your factorization, if you're your expansions, let's go for a common denominator here. We'll have k multiplied by k plus 1. They all have the common denominator, plus 2 plus k plus 1 here, all divided by 2. This will be a square bracket, sorry, and this will give us k plus 2 multiply k plus 1. I expanded this. You don't actually need to expand this, but I expanded it, and anyone who really likes like factorization can do this step. It's just a little bit long-winded, but what we have is that the left hand side, which was originally this, is now looking very close, actually not very close, exactly the same as the right hand side. This is the right hand side, so left hand side is equals to right hand side. This is exactly what we need. And so with this step, we can conclude that after the 3 steps here, by induction, that is true for all numbers that are positive integers, basically. The base case established that n equals 1, which is true. The inductive step show each case, which also is going to imply the next. And so this is by definition, every domino will fall. It falls. So 3 things that students are going to lose marks for, because this is a pretty lengthy solution, is that if you are going to skip the base case, you will lose marks. Without it, you never pushed the first domino, so remember to have the base case. Second, you are not clearly stating the hypothesis. If you skip the second step, or if you write the second step, if you did not show like a clear hypothesis, examiners see that and they go, well, we really need to see something that you assumed, so something like this is really needed. So that's the third thing. And number 3, jumping to the answer without showing the algebra. This is a proof problem, so you need to show like the full algebra here. You do also need to like write out like by induction, true for all that. It's a little bit annoying, yes, but you should have to show every substitution, every common denominator, every factoring step to gain maximum points. And even if you don't want maximum points, even if you show parts of the algebra, you get some points. That should be fine. So it's a 3 box process. It's 3-step process. In the base case, there's assuming for k, and there's proving for k plus 1. State what you assume, and then show what follows. In the final video, or not really final, it's more of like the next video, I will be moving on to 3 dimensional vectors and the dot product. Good luck, and I'll see you there.